Hi all, welcome back to our GDC, that is GPAT discussion center. In today's class, we are going to see about hybridization. Hybridization, okay. And in this entire tutorial, we are going to cover three concepts under hybridization. Those are definition, how this so-called hybridization is going to happen. That is, we are going to see this with the three different types and what is the outcome of this hybridization. These are the three important topics which we are going to cover in today's tutorial. So with this basic introduction, myself Dr. Nagaprashant, and now let us enter into our definition. So my dear GPAT aspirants, hybridization is a phenomenon in which atomic orbitals of different shapes and more or less same energy level will be intermixed to generate or give out the same number of hybrid orbitals of same shape and equal energy is called as hybridization. And one more benefit of this hybridization is the repulsion between these orbitals will be also minimized. So what exactly does it mean is the way, the orientation, shape, direction of these orbitals will also be placed in such directions, angles or axes so that these both clashes will be minimized. That is, the repulsive forces will be minimized. So obviously, when the repulsive forces were minimized, the energy of the atom will be minimized and so it attains more stability. So ultimately, let me come back again to the same concept of hybridization. That is, in hybridization, one or more number of orbitals, atomic orbitals, will be mixed together. And before mixing, the two things which we have to observe is one is those will be of different shapes and another one will be those will be of energy levels which are more or less near, that is not same, exactly not same, those are different energy levels. Okay, such different shaped nearby energy level atomic orbitals will be mixed together to generate same number of orbitals. If, for example, if four orbitals are mixing together, again it will generate same four numbers. The number won't differ. But after hybridization, the shapes of these all four, or how many are generating, how many are intermixing. Okay, the shape will be same after hybridization and energy levels will be same after hybridization. And apart from that, shape and energy, the repulsive forces between each orbital will also be minimized and so the stability of the given atom will increase. This is the basic concept behind hybridization and this is the definition of hybridization. Let me read out the definition of hybridization. Hybridization is a phenomenon in which atomic orbitals of different shapes and nearly the same energy intermixes to give the same number of hybrid orbitals of same shape and equal energy, and orientation of such hybridized orbitals be there that is minimum repulsion between these hybridized orbitals so that the energy will be minimized and stability will be increased. So, my dear GPAT aspirants, this is the definition of hybridization. Okay, so with this, let us try to go to the next part. And as we are in organic chemistry, especially pharmaceutical organic chemistry, that is the reason why I have taken carbon as example for today's thing. As we know, the name of the atom is carbon and its atomic formula is C. And three different types of hybridization are possible in particularly carbon. Those are sp, sp2 and sp3. Okay, this is the comparative chart for your easy memorization. That's it. Okay, and all these three different types of hybridization we are going to see in detail in next coming minutes. And as I said, carbon can participate in three different types of hybridization, that is sp, sp2 and sp3. If carbon is participating in sp, that is one s and one p will be mixed to generate two sp hybridized orbitals. The number is very clear. S is 1 and P is 1. So 1 plus 1, 2. That is, two orbitals are participating in hybridization. And so if carbon is participating in sp hybridization, then the bond angle will become 180 and its shape will be linear. Okay, this is about sp hybridization. Now let us come to sp2 hybridization, where 1s and 2p orbitals will be participating in hybridization. Total it will become 3, that is, 3 orbitals are participating in hybridization to generate 3 sp2 hybridized orbitals. In such case, the bond angle is going to be 120 and the shape of the carbon, especially the hybridized orbitals, is going to be trigonal planar. And the third type is 1s and 3p orbitals. Upon summation, it will be 4. So total 4 orbitals are participating in hybridization to generate 4 sp3 hybridized orbitals, and in such a case we are going to have 109.5 degrees as bond angle and the shape is going to be tetrahedral. So this is the summary of hybridization in a carbon atom. Let us see all these types in detail now. So let us start with sp, as here we have started with sp, and after completing sp we will be seeing sp2 and later we will be seeing sp3 in detail. Let us see. Let us jump into sp now. So before jumping into sp exactly, let us have an basic idea about the electronic configuration of carbon in ground state and excited state. In ground state, you see, we clearly know that the carbon's number of electrons are 6. Total 6 number of electrons should be there in carbon. What's going to happen is, in 1s we are going to have in 1s we are going to have 2 electrons, and later in 2s we are going to have 2 electrons, and later in 2p we are going to have 2 electrons. So totally, that is, here 2 electrons, here 2, and here these 2. So 2 plus 2 plus 2, 6. The total number of electrons are satisfied. And now when we are going to discuss about the ground state and excited state, we are going to considering only outermost orbital. We are not considering the first orbital. In particular carbon, the electrons are occupied in two shells, K and L. In K shell, we are going to have the so-called 2s. 2s. Okay, so we are not considering this so-called K shell, and we are going to consider only L shell. In L shell, we are going to have this 2s and 2p together. So we are going to see only the electrons which are present in outermost orbital. So that is L shell. Fine. So in outermost orbital there are 4 electrons, as we can see. In 2s there are 2 and in 2p there are 2. So total 4 electrons are there in outermost orbital, that is L shell, in 2p and 2s. And if you see here, 2s is having 2 electrons, whereas 2p can be divided into 3 subshells, that is 2px, 2py, 2pz, 2px, 2py, 2pz. So what's exactly happening at ground state is 2px is having 2px is having 1 electron, 2py is having 1 electron, and 2pz is having no electrons at all. So what exactly happening because of this is one subshell is having 0 electrons. One subshell is having 0 electrons, and this is resulting in high instability in our carbon, and so to prevent this, the concept of hybridization is going to apply here. And before applying hybridization, an atom should be in excited state. That is, a small amount of energy will be supplied to our carbon, and this particular one electron which is present in our 2s will be jumping to 2pz. So one electron from here has jumped to 2pz, and so now you can see one electron in all subshells. See, one electron in 2ps, one electron in 2px, one electron in 2py, one electron in 2pz. So equal distribution of electrons has happened here, and so now it will be very clearly having more stability. And at this particular point of time, we can apply hybridization concept. And let us see what's going to happen for this upon applying hybridization. And wherever we are talking about hybridization, we are going to talk only about this excited state of carbon. We are not at all going to talk about this ground state of carbon. No, we are not considering ground state of carbon. Not only carbon, any atom, if it want to participate in hybridization at ground state, it won't happen. It will happen only at excited state. Even these all are going to be very important points for your GPAT. You can expect a question from any of these points. So you should be very clear, and you should be keep on noting all these important points. And let us see. In case of sp3 hybridization, 1s and 3p, that is 3 px, py, and pz are mixing to form sp3 hybridized orbitals. You can see 4 sp3 hybridized orbitals over here. That is 1, 2, 3, and 4. So total 4, and its shape is going to be tetrahedral. In case of sp2, that is 1s and 2p orbitals are going to participate, that is px and py, and it's going to generate 3, 1, 2, and 3 sp2 hybridized orbitals, and its shape is going to be trigonal planar. In case of sp hybridization, 1s and 1p is going to be participated to form 2, that is 1 and 2 sp hybridized orbitals, and its shape is going to be linear. So let us see in specific one by one here. And here you see 1s and 1p orbitals are going to participate in hybridization, and this particular electronic configuration is excited state of carbon. Only 2, that is 2s and 2px are mixing, that is hybridized to form 2 sp hybridized orbitals. Here you can see the shape of 2s is spherical, whereas 2p is dumbbell. Whereas here both has intermixed to generate an equal shape. It's not spherical, it's not dumbbell. It's not spherical, it's not dumbbell. It's something else, and the shape of both of these is same. And you see the remaining 2 which doesn't participated in hybridization are same as such. That is dumbbell in shape. That is 2py and 2pz. Okay, and it's going to happen in ethine, very best example, and its bond angle is going to be 180 degrees centigrade. Let us see how the molecular orbitals are going to be arranged. That is, these two hybridized orbitals are arranged linearly. You can see one orbital in this shape and one orbital in this direction. So you can see this orbital has been placed here and this orbital has been placed here. Whereas these two unhybridized orbitals are placed here. One orbital has been placed here and another orbital has been placed here. Okay, so this is how an sp hybridized carbon atom is going to be looking. This orange shape is nothing but these orange color orbitals are nothing but hybridized orbitals, and this blue color shape are nothing but unhybridized orbitals. For your easy differentiation, these colors has been given. And now if you see this so-called one hybridized orbital has been here. Two such carbons came. And one hybridized orbital of one carbon has been bonded with spherical oneness of hydrogen, and the same happened with another one. And here, in both the cases, one hybridized orbital is vacant, and both of them are bonding together, overlapping together to form a sigma bond. Sigma bond is nothing but direct overlapping. Direct, that is, physical interaction will be there. Physical interaction will be there in between both of those orbitals. That's why it is called as sigma bond. Whereas if you consider a bond, interaction will be happening in between. An interaction will be happening in between these two unhybridized orbitals. You see, these two unhybridized orbitals are nowhere directly overlapped. These are called a side-by-side overlapping. Those won't be having any physical interaction. Directly, those won't be in touch. Those are called as side-by-side overlapping, and that is the reason why those are called as pi bonds. Two such bonds are going to be formed. One is from this orbital to this orbital, and another one is from this orbital to this orbital. Another one is from this orbital to this orbital. So two such pi bonds were formed, and you can see that here one sigma bond and two pi bonds. Totally three bonds are there in between our carbon and carbon, and that is called as ethine. That's what we have shown in our previous slide. That is, ethine is going to be the best example for sp hybridization, and that's what we have seen it here. And now let us come into the next type of hybridization, that is sp2 hybridization. Here you can see three bonds, three orbitals were participating in hybridization. That is one orbital from 2s and two orbitals from 2p, that is 2px and 2py. Total three orbitals are participating in hybridization to form three hybridized orbitals. That is three sp2 hybridized orbitals, and one orbital which didn't participated in hybridization is going to be as such, that is unhybridized orbital. So upon completion of sp2 hybridization, the carbon atom is going to have total 4 orbitals, out of which 3 are hybridized orbitals, that is sp2 hybridized orbitals, and 1 is going to be unhybridized orbital. So 3 plus 1, total 4. That is what we are going to see in sp2 hybridization. And after completing, we are going to get trigonal planar in shape, and the bond angle is going to be 120 degrees, and the best example is ethene, and the best example is going to be ethene, that is CH2 double bond CH2. And let us see how these orbital arrangements are going to be. This is how, as we know, there are three hybridized orbitals, and these three hybridized orbitals are going to be placed in a planar shape. Okay, in a planar shape, in a single plane. One orbital is going to be in this direction, one orbital is going to be in this direction, and another orbital is going to be in this direction. In a single plane, we can see 1, 2, and 3. Okay, and that same unhybridized orbital is going to be straight. If this is the plane where we have three hybridized orbitals, and our unhybridized orbital is going to be placed at exactly 90 degrees centigrade for this plane. This is how the arrangement of orbitals after hybridization is going to be, and it's very clear. Two such carbons are we are considering. Okay, and in each carbon, two hybridized orbitals are bonded with the carbon, and same is the case here too. And one hybridized orbital in carbon 1 and another hybridized orbital in carbon 2 are going to be linked together with a sigma bond. That's what we can see here, a sigma bond. And these two are going to be interacted with a pi bond, that is side by side overlapping, whereas sigma bond is direct overlapping. Okay, and whereas a pi bond is side by side overlapping. The same I have tried to show you in another type of representation too. Here you can see that in a plane where total 6. Why I'm telling 6 is because 3 hybridized orbitals of one carbon and one more 3 hybridized orbitals of one more carbon, total 3 plus 3 6. That's why I'm telling 6. 6 hybridized orbitals are in a single plane, whereas 2. Why I'm telling 2 is because one hybridized or unhybridized orbital from this and another unhybridized orbital from this, total 2, or in 90 degrees to this plane. This is what we can see, and the bond angle is going to be 120 degrees centigrade. Here it was clearly mentioned the bond angle is going to be 120 degrees centigrade. So with this, we have got a good idea about sp2 hybridization. Now let us jump into sp3 hybridization, where all the 4 orbitals which are present in L shell are going to participate in hybridization. So that is 1s and 3p. 1s and 3p orbitals, that is total 4 orbitals, are going to mix together to form 4 sp3 hybridized orbitals. Okay, and the bond angle is going to be 109.5 degrees, and the best example is seen in methane, CH4. And let us see how these orbitals are arranged and how the bonds are formed. So this is how there are a total of 4 hybridized orbitals, and all 4 hybridized orbitals are arranged in tetrahedral shape, where each and every single orbital is going to bond with 4 hydrogens and to form 4 sigma bonds and CH4, and the bond angle is going to be 109.5 degrees centigrade. Not centigrade, sorry, 109.5 degrees. So with this, we have completed all 3 types of hybridization, and the very important points to be reminded for this particular class, that is hybridization, is total 3 different types of hybridizations are possible in carbon, that is sp3, sp2, sp. And based upon the type of hybridization only, the structure and reactivity of carbon is going to be decided. Hybridized orbitals are formed by mixing of orbitals where electrons are mostly in excited state, not in ground state. That's what this point is mentioning. And different types of hybridization influence the bond strength and structure of the molecule also. So with these important points, I'm very thankful for you for your patience listening. If you are having any doubts regarding this hybridization, please ping to us so that we will revert to you back. And thank you for listening our class. Thank you a lot, and let us meet again in our next session with a new topic. Thank you.